Hi everybody, I'm Babak Salimi. I'm an assistant professor at HTSI. Today I'll be talking about applications of causal inference in the context of responsible and reliable data science. Good news is I'm not a machine learning person, not an AI person. I'm a data management person. I work in databases, so this means no maths, no fancy pictures. I'm just going to show you a bunch of cute animal icons. At HTSI, I'm the director of the Responsible Data Management and Analysis Lab. And in our lab, we look into some of the most urgent and important problems in data science, namely, how can we make sure that the insights that we get out of the data science pipeline, they are fair, reliable, and valid? How can we ensure that the entire process is transparent and explainable so that our conclusions becomes indisputable? And then how can we protect data from various types of data quality issues and biases throughout its life cycle? We look into various topics in this space, data quality. In this space, we're developing data cleaning algorithms to improve quality and integrity of data for improved decision-making and machine learning. Responsible data management in this context, our goal is to develop methods in order to protect data from various types of data quality issues that might be introduced throughout the data science and machine learning pipeline. Decision-making systems here, my goal is to democratize causal inference, develop data-driven decision-making systems that are easy to use, robust, reliable, and can be used by non-statisticians, people that are not sophisticated in statistics and causal inference. Explainability, we also have emphasized on explainability because it's important not for understanding data, but also for understanding various types of sophisticated machine learning models that we use in order to make sense of data. And then in addition to data management, our work is kind of grounded in causal inference because we believe causal inference can serve as a foundation for these topics, but we also contribute to causal inference. And the rest of this talks, I'm going to give you a brief overview of some of the past and ongoing projects that we have that employ causal inference for addressing some of these topics, and we also use insights from data management for improved causal analysis I'm going to discuss. Let's just start with explainable AI and fairness. During past few years, there has been a research of interest in explainable AI. The goal is very simple. Generate explanations, human understandable explanations for complex machine learning algorithms. But most of the existing techniques out there, for instance, you might be familiar with LIME and SHAP and their sort of variations. You might already use LIME and SHAP in your company. They merely focus on discovering correlation between inputs of a data-driven decision-making algorithm or machine learning model and its outputs. In a paper in 2021, we showed that this could lead to very sort of perplexing and wrong and misleading insights about how a machine learning algorithm works, simply because they focus on correlation. They only differ on how do they quantify this correlation. How many of you are familiar with LIME, for instance? SHAP? Okay, SHAP is a favorite tool in industry. Do not use SHAP. I can convince you after this talk. We have plenty of time to discuss that. They are only fancy way to measure correlation between input features and outcome. While LIME uses linear models to approximate correlation, SHAP uses this game theoretic notion of Shapley value. But at the end of the day, what they compute is correlation. To fill the gap, you can find several examples in this paper that shows that they could lead to highly misleading results. In 2021, we proposed LUIS, which is a causality-based framework for generating explanations for machine learning model, which uses this concept of probabilistic contrastive counterfactuals. These are causality basically at individual level. That generate explanations intuitively using a statement such as, what's the probability that changing an input feature changes the outcome of a machine learning algorithm from the observed outcome to a contrastive void or alternative outcome? This is the contrastive part. For instance, to what extent, what's the probability that if an individual change their saving from the current value to an alternative value, that would lead to their loan applications to be approved when their loan applications actually rejected. There are a lot of theories in cognitive science, psychology, and social sciences that this is how humans generate explanations. Explanations generated by human should be both causal and contrastive, meaning that we always explain things with respect to a contrast. Why this, not that? So from that perspective, Lewis is in line with those theories about properties for adequate explanations and how humans explain things. So using Lewis, you can generate explanations not only at individual level, but global level, and also contextual level. But more interestingly, you can generate explanations in terms of recommendations for users that what are the actions that they can take in the real world in order to be able to get the desired outcome from a machine learning algorithm. What is it that they need to do in the real world that can help them to achieve what they want? Sometimes we refer to these as recourse or counterfactual explanations, but this is from the causal perspective. So it's kind of a neat way to come up with a sort of framework that captures both explanations in terms of feature importance and counterfactual explanations. Okay, let me talk about algorithmic fairness. In the context of algorithmic fairness, the goal is to make sure that the decisions we make using data-driven decision-making algorithm, I don't know what happened, or machine learning algorithms are invariant toward individual sensitive attributes, invariant toward their race, gender, or age, or other protected attributes. But there's no consensus on how we should define this invariance. Most popular, there are tons of notions of fairness out there. Most popular notions of fairness use the language of a statistical inference in order to define this invariance. For instance, you may hear about statistical parity, equality of odds, equality of opportunity. All of them use the language of a statistical inference. But unfortunately, this language is insufficient to capture complexities and nuances behind the notion of fairness, which is a social concept. What's the role of causality in this context? Causality gives you a much more expressive language in order to capture insight that are not otherwise capturable with a statistical inference. So, for instance, you can say an algorithm is fair if, for instance, a particular sensitive attribute or protected attribute is not directly used by the algorithm, but it's okay if it indirectly affects its outcome. So we were among in 2019, we were among the sort of few first work that use causal inference to define fairness. But more importantly, we kind of showed that these causal notions of fairness, in order to enforce them, because the goal is to now make sure that an algorithm satisfies these definitions, in order to build machine learning models that are fair, we can we can reduce this problem into a data cleaning problem in which the goal is to enforce a bunch of conditional independence constraints that can be seen as generalizations of integrity constraints in databases. If you're familiar with functional dependencies or multi-value dependencies, conditional independence just generalizes them. So we kind of reduce this problem into a data cleaning problem and develop efficient methods in order to address that. Now let's talk about data quality and data cleaning. Data quality, improving data quality and data cleaning remains one of the most challenging part of the machine learning and data science pipeline. Despite decades of research in data quality management and data cleaning, it has been shown by several works recently that applying automated data cleaning algorithms, not only they don't help with machine learning, but in many cases they can hurt the performance of machine learning algorithms. They can introduce various types of biases, and they can actually lead to unfairness and discrimination. Why is that so? The main reason behind this is automated data cleaning methods, they ignore the process that leads to dirty data. They ignore the causes of data quality issues. And in many cases, we need to know the causes of data quality issues to see whether the underlying ground truth is actually recoverable from data. What you get using data cleaning techniques is the most likelihood state of data, which by no means it's at the actual ground truth. So it could be far from ground truth, even though it's the most likelihood one. What's the role of causal inference for data quality management? Using causality, then we can essentially model the process that leads to the dirty data. We can model the causes of data quality issues. And using that, we can come up with principled methods to reason about whether we can recover the ground truths using the available data and background knowledge about these data quality issues. And if the ground truth is not recoverable, how can we cope with it? How can we understand subset of sort of this data which is trustworthy and can be used for data analytics? And guide through how we can cope with this sort of incomplete information. We also have a bunch of ongoing work that look into data debugging. Here, the goal is when you deploy a machine learning model at production, so suppose you observe an unexpected behavior during production, the goal is to trace back these unexpected observations all the way back to their training data or all the decisions that we made through the data science pipeline. For instance, during data preparation, integration, feature selection, and so on and so forth that are actually responsible, but that's unexpected observation. That's the overall goal here. Next topic, causal relational learning. My colleagues already told you about two sort of mainstream framework for causal inference, potential outcome framework and parallel structural equations or causal models. But these traditional methods, they make a very simplifying assumption that we are dealing with a bunch of homogeneous entities. Everything starts with units of analysis in a statistics and causal inference, and they assume units of analysis are homogeneous. And then they also assume there's no sort of interference between these entities, which means these entities, they do not sort of causally interact with each other. By homogeneous entities, I mean essentially assume, for instance, we're dealing with a bunch of individuals, bunch of peoples, bunch of organizations. But look, this is how real-world data sets like. We have multi-relational data sets that are connected through key foreign key constraints. Suppose, for instance, we're interested to understand what's the causal effect, or is there any causal effect between authors' institutional prestige on, for instance, the review rates that they get from reviewers. Is there any bias going on in that context? This is a complex context in which we have heterogeneous units, we have papers, institutes, authors. It's not even clear what's the units of analysis, because if you see this schema, the treatment is in one table, and the outcome is in another table, and there is a one-to-many relationship between them. So it's a very sort of complex problem. How can we do causal inference in the context of multi-relational setting? We have a line of work that tried to address some of these challenges in 2022. I guess it was 2020. We introduced causal relational learning. It doesn't focus on estimation, it focuses on modeling part. It essentially combines data log, which can be seen as a subset of first-order logic. It combines it with structural equations to give an account, to give a language for specifying data generative process in the context of relational domain. When it comes to relational data, using first-order logic is somehow inevitable. We need that expressive power. We have to go beyond propositional logic. So it provides this sort of expressive language in order to specify what we know about the relational domain and come up with sufficient conditions for identifications. Last year, we introduced Hyper. It's a system for answering what-if queries and how to queries in the context of relational data. Here, the goal is just to democratize causal inference in practice. Using Hyper, you can answer sophisticated what-if queries without knowing anything about causal inference. The idea is you can use your sort of your beloved analytical SQL queries that you use in your everyday life in order to make sense of your data, generate reports, and so on and so forth. And then, for instance, if you want to answer simple questions such as what would be the effect of increasing prices of, for instance, Asus laptops. So suppose that in that hypothetical work that if we increase the price of Asus laptops on the average rating of Asus products in general, okay? So using Hyper, you can specify with the SQL query that compute the average user rating of these products. And then I specify this hypothetical scenario. And what it does under the hood, it's going to basically combine causal modeling with probabilistic databases in order to compute the answer to that SQL query in a counterfactual or hypothetical world in which the prices of Asus laptop is actually 10% more than the current values. We need probabilistic reasoning here because of this collateral effect of these updates on the other attributes and tuples. We also have an ongoing project in which we use graph neural networks and double machine learning. This one focuses on estimation, not modeling, for estimating causal effects from relational data. Baharan, who's here, is leading that project. Double machine learning is a sort of a state-of-the-art method that provides this recipe in which we can use machine learning models that are very good at handling high dimensional data for sort of sound and robust causal analysis. Let Yelena tell you about that. And the last topic that I want to discuss is causal enrichment for data enrichment for causal inference. Sound and robust causal analysis, this is my last slide. Sound and robust causal analysis rely on two assumptions. All of my colleagues, they kind of already make that assumption. And the first one is we have high quality data that contains all the relevant attributes that we want for causal analysis, or all the relevant covariates. And the second one is we have sort of reliable assumptions that are required for doing causal inference in the context of pairs causal models. We use essentially the language of graphs or graphical models in order to encode those assumptions. But most of these fail in practice. Existing data sets in, for instance, healthcare, education, and business data, they are not ready for causal analysis. This is the project that I collaborate on with folks at MIT. And the goal here is a data management project, it's a data management for causal inference project. What it does, it essentially integrates a particular data set with external data sources, for instance, external knowledge graphs or external open data lakes, governance data, semantic ontologies. We have lots of those resources in order to integrate or bring in features or attributes that actually they can facilitate causal inference. This is a very sort of complex task from the data management perspective, because like linking entities from your data set with external knowledge graphs, for instance, DBpedia is a complex thing, feature engineering and feature extraction. When you want to integrate your data with external open data lakes, you're dealing with data lakes that consist of millions of tables. Data discovery is a sort of big challenge. And finally, doing feature selection or causal feature selection in a situation in which we have hundreds of features, more features than data points, it's also very challenging, both from the statistical and from the computational perspective. And I know many of you are excited about ChatGPT and language models. We use language models in two ways in this project. First, it turned out that they're very useful. They could be very useful for extracting or learning causal models from data. So the idea here is in a 2023 paper, we developed a hybrid algorithm that use existing data discovery or causal model discovery from data and make query to GPT-4 in order to learn causal models. It turned out that does a very good job. It's not surprising, it has this background knowledge. And a second sort of applications of language models is actually for data enrichment itself. It does a very good job for contextualizing categorical data in particular, which could be useful for both causal inference and downstream machine learning tasks. Finally, we also work on summarizing causal graphs. So, like I said, and like what my colleague said before, causal inference fundamentally required background knowledge. It's a human-in-the-loop process at the end of the day. Fundamentally, we need background knowledge when we do causal inference. And causal model is a very sort of neat way in order to elicit this information from domain experts. But now suppose we're dealing with a causal graph that consists of hundreds of attributes, not even comprehensible for the domain scientists. The goal of this project is essentially to come up with a summarized versions of causal graphs. in which the goal is to preserve as much information as possible and guarantee that the summarized graph is still useful for a causal inference, which means you can still use it for coming up with sufficient or necessary condition for identification. We showed that this problem is NP hard, and we're currently developing approximate algorithms in order to address this challenge. And thank you so much for listening. That's what I had to share.